Hello, everyone. I'm going to be presenting a talk around real-time machine learning. Um, I'm Max Halford. Um, so I enjoy all aspects of data. I suppose I'm more of a data scientist, but I like to work with data in other ways, and I don't mind doing analytics and engineering and research. Back when I had time, I did Kaggle, and I was a Kaggle competitions master. But I've also been doing a lot of open source through the years. I write about that in my blog, and something I enjoy, that I still enjoy doing.
Mm.
And what I'm going to talk about today is the result of what I've been doing on the side for a few years, and it's becoming something a bit more concrete. Before delving into real-time machine learning, I want to just give an opinion about what I think how machine learning is doing today. For me, it's quite clear that machine learning in companies is maturing. I think that more and more companies are actually doing machine learning production, and there are many more success stories every day. Um, here, there's many ways to describe it. I've put four pillars and some concepts around each pillar. I think that historically we've been very good at doing model training, and that could be locally. But now we have tools like MLflow and SageMaker and many other tools to train models. And the once a model is trained, we want to deploy it, and we call that inference. And we want to sometimes do this inference online, so when in a real-time system. Um, so in that regards, we deploy a function in a way, and it's something that computer science has always been quite good at. I'll just take a chat. Hello. And yeah, feel free to ask questions through the talk if you want to. I'll check the chat. Um, I've seen many companies recently pop up in the area of monitoring. So it's not enough to deploy a model, it's also important to check the health of the model. So sometimes you see tutorials or blog posts about they train a model, they deploy it, but they don't really explain how, what are the next steps, how do you maintain it, how do you make sure that it keeps performing at an adequate level. And then if you do all that, then you also want to create a feedback loop, and all your new data that's coming in, you want to label it. That could be through active learning by only labeling the samples which are hard. It could be via some annotation tool, and maybe you have natural labels, or maybe you have labels that need to be provided by a human. And all this creates a feedback loop, and the holy grail for any company is to put this in place. And I don't think we're there yet as a community, but it's definitely something that's maturing, and you do see patterns starting to emerge. What's clear to me is that most of the time, all this is done with a batch mindset. Well, so batch, what does it mean? It means that models are trained on an historical data set and are deployed. And if you want to update your model with new data, then you typically restart training from scratch. So I've always been very curious about why this is predominant and why everyone does it. I think it's historical. It's the main way to train machine learning, and so it's comfortable right now. And there's a kind of a self-fulfilling prophecy where we learn at university and then we go on to teach in our companies, and then it creates like an echo chamber where everyone's doing batch learning. So I don't think I rarely see people who do real-time machine learning because batch learning is just so predominant. But what I've always been curious about myself is that when I was doing Kaggle competitions or when I was at university on research, the models I was building were static, but I was very aware that the environment to which I was applying these models was dynamic. So an environment can be anything. It could be a camera, it could be any sensor that's capturing data, it could be a website, a feed. And this environment is alive. It's always sending data, and we might want to make predictions for it. And then at some later point in time, it's going to yield a label, a ground truth. And the models that we build right now they don't learn from this ground truth straight away. We store this ground truth in a database, and then periodically we train the model. When I was younger, I always imagined that AI and robots were systems that would keep learning. So, maybe when Deep Blue was playing against Kasparov, I was expecting it to be learning against Kasparov while it was playing, between each game. But it doesn't do that. It's trained in batch, and it doesn't learn in a way. It's static. So the first thing I want to make clear is that inference is different to learning, and that's very much true for real time. So a lot of companies are getting better at doing real-time inference. So that's just making predictions with model in real time, as opposed to making predictions in batch, which is maybe a bit more comfortable and easier to do. The reason why inference and learning is very different with regards to real time is that real-time inference involves a model which is pure in a way. It's just a function that you can scale. You can deploy it to multiple servers. You can deploy it to devices, and it keeps on. It just in a way. It's just a function. Whereas with learning, there's state to manage. Your model has to update itself, and you have to synchronize your model across multiple servers, multiple devices, and that's much harder to do. And so before ever considering doing real-time learning, you always have to wonder, do I need it? It's not necessarily something that every company needs to do. But I have seen, in my experience, and I see it every day, a growing need for real-time learning. So there's many examples. A good example I had recently is that I have a new friend or colleague, I don't know what to call him. He worked at Netflix, and he worked on the recommendation system team at Netflix. And what Netflix does now is that every night they train a recommendation model per user. And so every night they learn the user's preferences. But what Netflix wants to do now is, while you are browsing Netflix, they want to learn from the signals that you're sending. So they've given you recommendations, but maybe tonight you don't feel like watching the recommendations they made for you. So in real time, you're scrolling the page, you're ignoring movies, you're saying no, you're disliking. And so they would like to have a model that constantly is learning like that. And maybe it's retrained every day, but during the day, it keeps learning. And it's the next frontier in a way. So it's probably the icing in the cake for some companies. But in other situations like trading, high finance trading, having models that are as up to date as possible is actually meaningful. So yeah, it's always a good question to ask: do you actually need to do real-time learning, or is batch learning every day, refreshing model every day, is that sufficient? And so that's why I call real-time a weasel word. Now, weasel word is just a word that there's no single definition. It's a bit it doesn't convey any sense. The answer is that real time, with regards to machine learning and data science, it really means what you want it to mean. For some people, retraining a model every 15 minutes. So I know a finance company that does this. That's real time for them. That's good enough, and they're happy.
Yeah.
But for some companies, they want to be doing that faster or slower. So yeah, it's interesting to discuss like what is real time for you or your company. And indeed, at the end of the day, what matters is, does this real-time model, does it actually have a business impact? So again, batch retraining might be enough. And I really want to insist on this point. So I've never been in the business of trying to convince people that online learning is the only way to go. I think it's just important to understand the differences. But it is the talk about online learning, so I will talk about it. And I just want to say that with regards to batch learning, there are some downsides. It's wasteful because every day, if you're retraining on all the data that you have, well, it doesn't feel right in a way. So not very good in terms of cost, in terms of time, in terms of friendliness to the planet in a way. You have to decide on a schedule, and you could have stakeholders that are always going to keep pushing you to, reduce the retraining time. So that's going to involve some, maybe some very high compute power, and maybe that's not adequate for the job.
Mm.
You know, it might start feeling weird to retrain a huge model every 50 minutes. I don't think that's sufficient. And I'm also going to talk about something called online batch parity. And I have another slide on that to explain that later. But
Just one question, Max, because
of course.
I had a discussion this week with somebody, and we were talking about ML ops, right? And about when you retrain a model, then people are getting nervous that, the accuracy or whatever, the quality of the new model might not be matching the previous one and so on and so forth. So there's a need, right, to be a bit, how should I say, people or business want to control more or less, right, the model. So if you're real time, how do you control, right? That's maybe a reason why there's some resistance. I don't know. What's your view on that?
Yeah, no, I completely agree.
Especially,
I'm going to talk about this a little bit later, but
yeah,
it's an interesting topic. Yeah,
yeah,
for sure. Yeah, no, the idea is that if you keep training a model, it might do catastrophic forgetting, or it might not be performing as good.
yeah.
The short answer is that you should always have multiple copies of your model. So the model right now, the new model that's trained on new data, and if possible, both models should be competing, and you should be able to monitor the performance of both models and to have observability on the system, for sure. There might be cases where the new model is performing better. There might be cases where it's overfitting to the new data. So it depends. There's no free lunch. So yeah, the alternative to batch learning is to do online learning. And in online learning, the model does not have to restart from scratch, and instead it can process at minima a single sample of data and update its state. And so there's a life cycle to this. The idea is that if you're doing online learning, it's very different to batch learning in the way you do things. The idea is that you don't train a model offline and deploy online. All this is done online. So here I have a rough schema, but I'll just walk you through it. The idea is that here we have maybe a simple example. We're at Netflix and a user starts a session that triggers a request, and maybe we're predicting something like, do they like this movie, or what's their mood, something like that. So for the task that we're performing, we're going to fetch features. So in real time, we access features for this user, and that's going to trigger an inference. So in real time, we do a real-time inference, and this inference, we store it. And at some later point in time, the ground truth is going to become available. And that could be, did the user click on the movie, or what movie did the user choose, or something like that. So there's a delay between the moment when you produce a prediction and when you get the label. So the label, the ground truth here, we receive it later, and that allows you to do monitoring. So you've made a prediction in the past, and now you have the ground truth, you can compare the performance. And the great thing here now is that the features that you extracted to do the prediction, you can match them with the ground truth now that you've received it, and that provides you data for learning. Now, the great thing here is that the features that you have, you do not have to regenerate them when you get the ground truth. You already have them because you use them to do the inference. Now, the beautiful thing here is that these features are not corrupted. There's no leakage in them. You obtain them at the moment of inference. If you are to re-obtain them now that you have the ground truth, you're risking to introduce leakage, because what you want is to have the features that are representative of what we know about the user at that point in time. So that's called online batch parity, and I'm going to do another slide on it because it's an important concept. So the benefits of this is that it's efficient because every sample is only processed twice, once for doing a prediction and once for doing the learning part. It's not every day where you repeat, you don't see every sample every day. So your model is as up to date as possible. You don't have to schedule a retraining. Online batch parity is ensured. So this idea of always using features for training which are actually representative of what we knew at that point in time, what was true. And that also allows you to do back testing. So I explain that a bit afterwards, I think. Yeah, I'll explain that afterwards.
Mhm.
So to finish on online batch parity, um, I'll just repeat what I said. The idea is that when you're training a model, you want to make sure that the features that you're using for training will be available when you deploy your model. And one of the great problems with deploying models right now is that you train a model in a notebook or in MLflow in your local environment, your laboratory. And when you deploy it online, you realize that maybe the features that you were using offline are not available in real time because of delay, because you have an ETL that's calculating features. It's not ready. It's not supporting real time. Um, so people get bitten by this, and every time the feature maybe it sounds too good to be true because you don't have access to that information or whatnot. And the idea here is to reverse that process and to instead um, generate predictions online, generate features online, and use those both for inference and for training. Now, there's this blog post, and I'll share the slides afterwards so you can get the link. There's this company called Fair, which is fairly recently new in the US, and they do this. Their machine learning team does this. They deploy features. So they have logic to generate features in real time. And for 2 weeks, they just collect these features, basically. And in 2 weeks afterwards, they have 2 weeks worth of features that have been generated online, and they use those features for training. And so they know that the features that they're using for training are features that are available because that's the way they were produced. And it's interesting because they don't use features that they build locally in their notebook. So they always have to wait a week or two. But the great thing by doing this is that so you could say they're slow in a way because they have to wait for 2 weeks. But at least they are using features they are sure that can be used in production. So that's really interesting, I think. And I see more and more companies starting doing this. So it's interesting to think of the difference between offline and online features. Now I want to talk too about progressive validation because I talked about being able to reproduce to do backtesting. Now you're very used to cross-validation, supposedly. So cross-validation is you take a data set, a historical data set, you split it in parts, you train on a few parts and you test on the other part. Progressive validation is different. Your model is able to learn online. So what you do is that you take a data set and each sample, you loop over the data set, and for each sample, you first do a prediction. And then afterwards, you make your model learn on that sample. So each sample is first predicted and then you learn on it. And the great thing is that the predictions are made when the model has not seen that sample. So you get two things. You get an out of four score. So you know the predictions for your model for each sample before the model is trained on it. And also your model has trained on all the data. So that's really interesting. And so it's the way you benchmark online models. And if you look at papers from Google in ad clicking situations, this is what they do. What they do and actually is beyond this. On top of being able to do progressive validation, you can do what's called delayed progressive validation. So instead of looping over your data set in the order in which it's set, and maybe it's ordered by timestamp, you actually take into account the delay. So when you see a sample, maybe the sample is whether or not someone clicked on an ad. Instead of just predicting on it and then learning from it, you wait till the user would have clicked on it. So maybe it took 5 seconds. So during these 5 seconds, you also predict for all the other samples that are before that event, that click event. So the result basically is that you're processing your data in exactly the same order as happened in production. Because in production, it's a sequence of predictions and of clicks. And essentially here, what we're saying is that you can do offline, you can reproduce that sequence of predictions and on clicks. And this is great because it's a correct way to evaluate a model offline. And it's not something you can do with progressive validation. And here I put a link to a blog post that I wrote on that goes into further detail on this. So I know I'm bombarding you with a lot of concepts, and here's another one. So there's one thing interesting to think about, and I think it refers to a bit to what Patrick was saying. There's something called stability plasticity. So this is general, it's not just for machine learning, it's also for us. The idea is that plasticity is this notion of being able to learn very rapidly. So you meet new people, you remember their names maybe. And stability is memorizing previous knowledge. So um, maybe you're not so good at learning in real time. And a good online model is a model that is finding the right balance here. So if a model is too plastic, then that's what leads to catastrophic forgetting. It only focuses on recent data. And it's interesting because maybe that's not a problem. Maybe that we don't need to be good on all the data that we've seen in the past. And maybe that having a model that is good on recent data is what matters. But maybe that's not true too. Sometimes you have situations where maybe you're going through days of the week and there's new data all the time. And maybe it's Tuesday today. So the 6 past days, you've seen Monday, Sunday, Saturday, Friday, and all that data is not representative of this Tuesday. So maybe you want to remember the past Tuesday 7 days ago. So when you design your model, you kind of have to always think about your model's going online. What do you want it to remember? Do you want it to remember the very recent data to be plastic, or do you want it to be stable and maybe stable in a seasonal manner? Maybe you want to remember data that is from last month, like the last 7 days, last year, etc. So there's a whole community of people that are doing continual learning and that discuss all these topics. So just some random side too. I always like to discuss them with people, but I'm always curious to understand why online learning is not more popular, because I don't think that it is. I think that these notions that I just explained, I don't always understand them well, and they're really hard to grasp and to teach and to actually benchmark and test. So it does require a different mindset. I also think that the data ecosystem in terms of the platforms that we use, or Snowflake and ETLs and whatever tools we're using at the moment, we've overfit to batch learning in a way. So it's very hard to do online learning with existing systems. So if you want to do real online learning, you have to actually build an infrastructure around that. So I also think that, well, the ecosystem is not as there's not as many popular tools around online learning, and we're also missing. So we all know, or I know that companies, the big companies, Google and all that, are doing online learning. It's very important for ad clicking and things like that, and finance too. But those companies keep it to themselves, obviously. And so we're missing some success stories from big companies. Go on.
Quick question: are they using River, or what do you know? Or do we know?
Well, I hear rumors. I hear some ride-hailing companies that I won't name that are using it, but they don't always just mention that to us. That's the problem with open source. But indeed, when I started to look into online learning 3 years ago now, I realized that there were tools like Vampire Rabbit and things like Flink, but I come from a lot of the Python world, and I was kind of missing a nice tool to do online learning and at least to experiment with. So at the time, I was always thinking about doing the scikit-learn equivalent of online learning. And so I started a tool called Creme at the time. It worked quite well, and it made me meet people. And I met the team working behind Scikit Multiflow. So that was Albert Biffet's research team, and we merged. It took 8 long months of negotiations to merge, because we had to redesign the API and convince them that maybe some parts of our code base were better than theirs, and vice versa. But we merged, and we're really happy about it. So now we have 3 core developers. So there's really 3 people who are working on the code base. So it's safe in a way. We know that it's something that's going to last. And we do know that some companies are using it. So some of them reach out through email and tell us that they're using it. And so we help them to do that. But we also know, well, obviously some companies are using it without telling us. I would be, I wouldn't want to be pretentious on this. I do think that a lot of companies are using this as in an experimental way, because it is not something that was hard to convince yourself that you're actually going to do online learning. There's so much energy behind batch learning, and there are so many reasons to not do online learning. Now, I'm not going to talk too much about River, the code in itself, and I'll just keep talking about other things, but I will show you a beginning example. So I have other presentations on my blog that go deep into River and how it works. But here I'll show the notion of progressive validation, because this is what it's doing. So here I'm defining a simple model, but which usually works quite well online. So it's a linear model, and there's a standard scaler. So this is a transformer that scales the data, and it's stateful. So this scaler, it's going to remove the average and divide by the standard deviation. And so those are counters that are maintained per feature and that can be updated online. So one of the great things you discover when you do online learning is that things like an average are statistics that can be updated online, and there's formulas for that. And well, there's a model and we have a data set. So I haven't shown here what the data set is, but it's basically a stream of data, and I'll explain what it looks like afterwards, but it's individual samples. So X here is a dictionary. And what we do is that we first produce a prediction with the model, and then we update a metric. And this metric is stateful. So you don't need to show all the data. It updates the value of the metric in real time. And then you update your model. And this basic dance around the data, here I'm doing it in a for loop in a script, but you could put this behind a web server. So you could have a web route to make a prediction, another one for updating the model. You can use this in any way you want. And in that sense, River is not a tool to impose a way of doing things. It's just a tool to do online learning. It's a toolbox. And one of the interesting things behind River is that we do not use the numerical data structures such as NumPy arrays or pandas data frames. We actually use Python dictionaries. And well, in terms of performance, there's a very good reason, is that when you process individual records of data, there would be huge overhead to be using NumPy or pandas. So if you're receiving data from a stream, then if each one of those samples is a pandas data frame or a NumPy array, then the cost of creating that data structure is prohibitive. And actually just using a native data in Python, a dictionary, is much more performant. I'll explain this a bit more afterwards, but we went with dictionaries because, well, we could have gone with lists, but the nice thing with dictionaries is that they have names, and they represent sparse data naturally, because a sparse data, if you think of a sparse array, you have to fill it with zeros. They're implicitly zeros, the features that are missing. But with a dictionary, just remove them from the dictionary because there's no positions. And the Python standard library is very well, it's very friendly towards dictionaries, and it's very easy to, and there's also a one-one relationship between JSON data and dictionaries. So it's very convenient to use River in a web server, in an application. So when you receive data through a payload, through like an HTTP request, you can very easily send it to a River model. You don't have to convert it to a pandas data frame or anything like that. Now, another thing with River, which is important, is that we encourage people to use pipelines a lot. There's deep reasons behind this, but the idea is that here we have you could say complex but not complicated model, which is taking in some raw data and which is doing some aggregation. So here it's going to extract some TF IDF values, and is also going to compute the mean price per user. So this is an aggregation. And the nice thing is that the aggregation can be updated online. It's a feature that it can actually be it's a class but which computes a feature but can be updated online. So the average price per user can be calculated online. And then we scale the data and we have some decision tree model afterwards. We encourage using pipelines like this because the model here, you can use it to learn, to predict, and all the necessary steps to manipulate each step is done for you, basically. Now, another thing about River is that, so River is, you could think of it as scikit-learn for online learning, which is ambitious to say because scikit-learn is such a great library, and I don't think we're there yet in terms of maturity, but the idea is that we want to be general purpose. So we support different paradigms and different functionalities. So I've shown you decision trees and linear models, but the ambition of River is to go beyond that. And recently we've added support for time series forecasting and anomaly detection. And there's, yeah, just many things that we are currently working on. I'll explain the roadmap that we have afterwards. Now, to come back to the question of speed, one thing that's nice is that a lot of libraries out there, they implement some sort of stochastic gradient descent. So a linear model that can be updated online. And that allows comparing different libraries in terms of performance. And so we've compared to other libraries on a task where the data is coming in through a stream, so one sample at a time. And this is where Viva shines because it doesn't cost anything to convert the data. We use the data as it is, dictionaries. And that is much faster than other libraries, which actually have to convert the data to their internal representation. Now, obviously, these libraries would perform better if we were comparing on a different task, which would involve mini batches. So maybe you have to learn from a mini batch of data and then do a prediction on a mini batch of data, etc. So we could call these huge data sets where you process data in chunks. And to be able to handle these performances, these data sets, you need vectorization. So the reason why NumPy and, well, libraries based on NumPy and Torch and TensorFlow are fast is because they use vectorization. And so this is not the area of focus of River because this is not what we're catering to. But some River models do support processing mini batches. And so the linear models, the standard scaling, the basic models, they do that. And so there's an example where, well, the people from Vax, so maybe you're familiar with Vax, but it's like a pandas data frame, but for huge offline data sets. They have an example where they process the New York taxis data set, which is 1.2 terabytes. And they have a script where they that builds a pipeline which processes the data, extracts features, scales the data, learns a linear model in 15 minutes. And they do that with 1.2 terabytes of data. So it's really, it works, and you can do that with River too. But it's not the focus of the library. It's just to show that it's actually possible. And so the question is, do people use River? And well, it's complicated because we're open source and we don't work directly with companies, so they don't have any obligation to tell us. But we do know that some use it. So one company I know, well, I can't name them, sadly, they do penetration testing. So they help companies secure their networks. So they're always sniffing for malicious traffic on networks. And the strategies that hackers are using to get into compute systems are always evolving. So they try to build systems which learn in real time. And for this, they discovered River because they wanted to do real-time learning. And we've been in very close contact with a few of them, and they're very nice to work with. So they've encouraged us to keep working on anomaly detection and things like that. And yeah, I always hear about rumors about companies that are prototyping with it. And sometimes we'll get some nice emails, and it's encouraging in a way.
Yeah. One question. I mean, one of the nice use cases you mentioned about Netflix, right? About movie recommendation. In fact, this is we did a small test with my colleague for banking product recommendations. The problem is that you might have new products, right? And for new products, you have no data at all. So the only way to integrate new movies, new products is to learn incrementally until you have enough data, because you cannot cover that with batch, right? Anyway, by definition, because you don't have the data. So
Yeah.
that's a nice use case, in my opinion. I don't know what you
I
think.
think so. I think that, well, in general, for any machine learning system,
Yeah.
when you're doing predictions in real time, well, for any system, basically, it doesn't have to be real time.
Mm.
When you don't have enough data, you probably want to have a safeguard rule, a fallback rule that uses a manual rule, basically. So
Yeah.
if your product has never been seen before, then you probably just want to try it out or have some manual rule that tries it. But then again, if we're entering the world of recommendation, then that's a different problem. But in that case, you want to use something like bandits or things like that. But yeah, there's a whole world and literature around those topics. But yeah, it's super interesting.
What I found interesting as well is that, okay, in this case, we were using multi-class classification, right? And the
Yeah.
nice thing is that you don't need to see all the classes before, right?
Yeah. Yeah, so I forget to mention this because for me it's natural, but all the rivers and the models in River, they don't make assumptions about the data. So they don't assume a number of features, they don't assume a number of classes. They just learn in a way. So if you show them a new feature, from one sample to the other, there's a new feature that's added or deleted, they handle that, they support it.
Yeah.
So we have unit tests to try that out, and we build that with in mind. And the nice thing about dictionary is that it's not bounded in size. You can just do what you want. And indeed, for multi-class classification, well, the stream of data is there. The model is initially doesn't know anything. The data is coming in, and it says, "Oh, this is a new class," and I'll deal with it. So, online learning is very much about being able to make no assumptions about the data. I think that's really interesting. That's true.
Why is it not so popular then?
Well, it's again, I think it's just we're not used to it. So I think that historically we've been doing machine learning in a laboratory environment at school or in notebooks in Kaggle competitions, and your environment influences what you build. So the tools that we've been building are catered around, well, being able to cross-validate a model or things like that. But then as a field, we matured and we started deploying models. And then we encountered friction. We encountered real problems which we don't see when we're doing Kaggle or things like Kaggle. So that's why now maybe, hopefully, I don't want to force it, but maybe online learning will become more popular because it just solves some pain points. It's not just a question of, is it better or more accurate, but it actually makes it possible to deploy models and with less engineering cost and less problems. Yeah. So we have a roadmap, and so the roadmap is public. So there's a link. It's a Notion Kanban board, but there's some things that I want to work on in 2022, and we'll see what the other developers want to do. But the penetration testing company that we've worked with, they want to work with graphs. So they have these batch models that work on graphs, and they like to see what they can do online. Recommendation system is a big thing. It always pops up. It's natural for people to want to do recommendation systems online. Recommendation systems are often based on bandits, and you could say that bandits are a special case of reinforcement learning. So we want to look into that too. We want to keep putting effort towards anomaly detection, but also time series. And yeah, in general, we have documentation, but we feel that there's a need to educate and not just show River, but also try to explain all these concepts. And I'll keep doing presentations and try to distill the knowledge. But if you have needs, and as a company or in projects, then feel free to get in touch. And we're always curious to find a product market fit in a way.
Just one comment. 6 years ago, I did my first machine learning course on Coursera. That was Andrew Ng, Stanford machine learning course, and this is the first time I heard about incremental learning, because he's mentioning incremental. How do you do online learning? You just do one increment. and that's it, right? But then I never heard about it before I stumbled across Craig.
Yeah. Well,
This is
yeah,
fun, right? This is
it's funny, right? But I think, yeah, I get a lot of emails because I think that when you type incremental learning or online learning, there's not a lot of results. So, you quickly find the usual suspects and you get in touch with them. Um, but yeah, maybe hopefully as a field it's going to expand or not, but it is curious that there's not more of it. I agree.
then the second thing, we were discussing tiny machine learning this week with a different forum, right? And somebody was asking, because one of the problem with okay, that's a totally different topic, but if you have to deploy, a model into microcontrollers that are not connected to the cloud, then what is the solution? And basically to deploy a model on a microcontroller that can learn by himself, right?
Yeah.
That's an interesting area as well, I guess.
Exactly. It's the difference I tried to mention between inference and learning, and you
Yeah.
do see a lot of I see the name TinyML pop up, but they only really focus on inference, and in
Yeah.
that sense, it's really easy because you're just deploying a function. It's literally just a function. It's not smart or it's not stateful. It's pure. And indeed, doing learning on real time on edge devices is much harder. And it's not something people focus on a lot, but it's super interesting.
It's interesting because I had this question from a colleague.
Yeah.
I found it quite interesting.
So for Christmas, I've ordered a Raspberry Pi, and one of the things I want to do is install River on one of those and try to make it run.
I would be interested to know how it works. Yeah.
Yeah, I'll probably write a blog post about it, or if it works, or if it doesn't, we'll see. But I want to see because maybe the code base has to be adapted, or some things have to change. But we'll see.
Max, I have a question regarding, because there's two notions here that you haven't mentioned really only incidentally, but it's about the people might think about this online learning and incremental learning online, and something like you say, okay, so you have some kind of a black box approach. That is something that in certain industries, something that they definitely don't want. Regulators are already saying that they are not going to allow for certain industries, unsupervised learning and so on. And in other industries, like for example, Patrick and me, we were exploring in the financial banking industry. I mean, these are people very really controlling to the extreme, and for them, even shooting a tweet over Merry Christmas, this is a control process for them. So can you imagine how it is going to be just deploying recommendations or deploying frameworks which do self-updating to the recommendation systems? No. So how do you see this? Have you already some encounters there or meetings with people who tell you what about transparency about these models? Can you predict what is the model going to learn or how it's going to react against some features? Or because they will always come up with the thing about the chatbot that it was there and it started to become crazy and they have to withdraw and so on. This is the first idea people come up.
Well, first of all, I don't think that I'm the best person to talk in terms of data governance and these questions about performance, but I think there's a huge topic around observability. So being able to just, tell if my model is doing well or not. Obviously, you can never tell how well exactly it's going to do before actually deploying it. You can do cross validation. You can test locally, basically, and that's why I'm saying that online learning is good because you can actually reproduce the production scenario in offline. But then that's all offline, obviously. Now, and you can be as good as you want and have as many PhDs as you want. You have to convince business stakeholders. I get that. Now, maybe the answer to that is that, well, regardless of if you're using batch learning or online learning, you need some monitoring system. So before deploying a model, you actually have to have a healthy, I don't know, dashboard or pipeline or data system to actually monitor your system. And then I think I would say that it's more likely for a batch model to go haywire or to degrade, at least in terms of performance. What's nice with an online learning model is that it always is stable in a way. It keeps learning, so it's always up to date. So there's less risk of it degrading. There is a risk of it spiraling out of control. But then again, normally you would test this locally. Now, anyway, if you are doing online learning, or the correct way to do to deploy models is never to have a single model that's deployed. You should always have copies of your model. So maybe the model, you would checkpoint it every day. So you'd have model today, model tomorrow, model yesterday. And all these models, they could be shadow deployed. So they would each of them would be doing predictions, but only one of them is serving the prediction to the user. And you have a way to just, well, measure the performance of all your models. So you can always in real time decide which model is performing best now. And if you see that one model is, so tomorrow's model is trained on new data, and you see that it's haywire, that is going crazy, you can always just say, well, the performance of over the last 10 minutes is really not good. Let's switch back to yesterday's model. And for that, you need a meta model, some strategy on top of all this to manage your models. And now I was going to talk about this. And so what I'm doing now is that I've recently joined a company in California. It's a stealth startup that is actually around online learning. And the goal is to build a platform that allows companies to deploy models. And well, deploying a model is not hard. You just create some API and whatnot. But this question of having multiple models running and having a model that keeps training is what we're doing now. And we are building a system which, well, automatically learns which is the best model and keeps it up to date. And you can also override it. So as a user, you can say, I'm looking at a chart of the performance of each model. And I can say, well, today I want to use this model because I'm scared of this new model. But it's basically what you do in software engineering is that you unit test, you develop a new feature and you unit test it, but sometimes it doesn't work. You deploy and you forgot something. And it's a big question. It's not just machine learning, it's software engineering.
Absolutely.
Yeah. And they've had this problem for years. So maybe we should listen to what they have. So their solution to this is to do canary deployments, A/B testing. And this is definitely something that you want to do in machine learning. It's a solved problem in a way. So let's not reinvent the wheel and let's just do what they do in software engineering, but for machine learning. And that's what ML ops is in a way. And ML ops is a very young field and it's maturing. But I do see more and more companies that are asking the same question as you. And the answer to that is that you can't have one model which is is going to perform well. You need to be able to roll back. You need to be able to A/B test, etc. So sorry, that was a long answer. But I hope.
No. Thank you very much. This is very interesting and enlightening regarding how to handle this and how to answer to clients in certain industry, because exactly they are totally afraid of that, and you have to tell them, explain them, look, we have to, there's not something that you create and you just put there, because if people they think that you're going to create some intelligent algorithm and just leave it there and that's it. But actually it is part of a new process, has to be integrated with the engineering of the operations, and then you have this ML ops, which is going to be critical for that, of course. Okay, no, thank you very much. Very enlightening. Thank you, Max.
I would say the short answer, is just to say that software engineering is older than machine learning, and they have these problems, and they've built an ecosystem around that and concepts. So it's good to listen to them. Just to bounce back on what you said about, it's not just about deploying a model, and it's actually about monitoring it. That's very true. So yesterday I read a blog post about a French company that they created their own data platform. So yet another company that's created a data platform. And the blog post goes from training a model to deploying a model, but it doesn't close the loop. It doesn't tell you what's the story afterwards. So, what happens in a month? Maybe the model is not good. What do you do? So it's baby steps and we'll get there.
No, I think industries, the clients, they need to learn that the same way they have to hire people to maintain websites and so on, they have to hire people for maintaining this new technology, because it is in a framework in itself. Before we're saying, let's build a web page and leave it there. Yeah.
No, exactly. In California, I've seen a new job pop up. It's called an inference engineer. So it's a machine learning engineer that is just focused on prediction. That's maybe responsible for this kind of thing. So
Yeah.
yeah, you can
Okay.
see that the field is very immature at the moment, but we'll get there.
We have MLOps engineers now, right? It's pretty.
Yeah, no, exactly. That's new too, but it's not something you learn yet. Everyone is just doing it their own way. But that's what I'm saying is that I think the field is maturing and that there are patterns that are emerging. So I think we summarized a lot. The takeaway for me is that online learning is nice in that it's a new tool, so it's complementary to batch learning and allows you to maybe simplify some of your processes, but it's young. It needs pioneers to make it work and to, it's not something that out of the box just works. So River is a good step in that direction because it provides you with algorithms and ways of doing things, but it doesn't take you to the end of the journey, and there's still a need for a platform or higher level systems to deploy models. So, and I think I always felt that that's too big of an endeavor for just me or a researcher. You need to be backed by a company or financing, or it has to be a full-time job. So that's why I started my new thing. But the company doesn't really have a name or logo yet. It's with 3 of us, so there'll be more news soon. So I'll share the slides, and here are some other links to some there's many things to keep reading, and then you can look at the links therein. An interesting thing is that there's this recent paper by Google, so the DeepMind team, who they wrote a paper where instead of training a neural network on the ImageNet dataset and doing epochs and training it over it multiple times and overfitting to it, they only allow themselves to see each image once, and that's online learning. So it's interesting to see where the field is going. So that's it. I'm done. Thanks.
Thank you so much, Max. Was pretty interesting.
Cool.
Yeah, we tried to speak for a long time, so finally we made it, right? So that's cool.
Yeah, sorry about that. Yeah.
No, that's really cool. That's an interesting domain, interesting area, right? As you said, not very popular because, I don't know, I don't see too many blogs about it, but I'm sure it's going to change in the near future, right? Let's see. But let's keep in touch, and if you can just send me the PowerPoint,
Yep.
that'd be interesting.
I will. Yeah.
Thank you so much, Max. I'll upload the recording on LinkedIn and YouTube anyway. So keep in touch and good luck.
Yeah, thanks a lot. Yeah, and good luck to you too, and thanks for the discussions, and I hope we keep in touch. That was nice.
Good. Thank you very much, Max.
Yeah, have a nice evening.
Bye.
Bye.
Thank you very much.
Bye.
Thanks. See you.
Bye.
Bye, everybody.